We can start. So, welcome to this afternoon session. It is a pleasure to introduce Chiara Toldo from Harvard University. She will talk about near extremal de Sitter black holes and GT gravity.
Okay, thank you very much. Thank you very much for organizing this workshop and inviting me to speak here. So I'm going to talk about some work that I did in collaboration with Alejandra Castro, which is a faculty in Cambridge, and Francesca Mariani, who was a master's student in Amsterdam, and now she's a PhD student in Ghent, in Belgium. So first of all, I will introduce the setup, and I will tell you why it's useful to study near extremal black holes, in particular near extremal black holes in de Sitter, what are their peculiarities. And I will introduce the concept of extremal and near extremal black holes, first in asymptotically flat space. I think that these are kind of basic concepts that probably you all know, but it's good to refresh your memory. And then I will tell you the generalities about Reister-Nordstrom, so charged black holes in de Sitter. I will tell you that indeed I will show you that they exhibit 3 different extremal limits, and this gives you a lot of a very rich physics. They exhibit 3 different near-horizon geometries, and we will study, in the context of JT gravity and the near ADS2, near CFT1 correspondence, the perturbations on top of this extremality, namely what happens to this black hole, how do these black holes react when you kick them out of extremality and you give it a bit of temperature. We'll see that they exhibit some very specific dynamics. And I will collaborate the analysis of the thermodynamics in 4 dimensions that I do here, also from the 2-dimensional perspective by analyzing the perturbation at the level of the JT gravity model. So first of all, let me start with a bit of motivation. So what is de Sitter space? Well, de Sitter space is a maximally symmetric solution to the Einstein's equation of general relativity with a positive cosmological constant that I denote with lambda, that in our case will be positive, like strictly bigger than 0. So there are observational and theoretical reasons at the basis of our interest in de Sitter spacetimes. So one is for sure the fact that the expansion of the universe could be driven by a positive cosmological constant, so like we have, for instance, nowadays. But also in the context of the holographic correspondences, for instance, in ADS-CFT, black holes provide a lot of valuable insights in the dynamics of anti-Sitter space, and in the same fashion, de Sitter black holes could indeed provide some insight or some more knowledge in the study, for instance, of the proposed DS-CFT correspondence, which is a holographic duality for de Sitter space. So there are indeed, so we are probably, all of us are used to, for instance, know the solution, for instance, the Schwarzschild solution, which asymptotes to Minkowski space. And we're also familiar with black holes in de Sitter, because indeed they are useful for the ADS-CFT correspondence. Black holes in de Sitter, however, they are slightly different from, they differ a bit from the other cousins with negative and 0 cosmological constant, because once you have a positive cosmological constant, you have a cosmological horizon. And this cosmological horizon indeed is a horizon that lies outside the black hole and bounds the size of the black hole and bounds the size of the de Sitter black hole. And since it's a horizon, a cosmological horizon also is treated as a thermal entity, meaning that it's characterized by its own thermodynamics and its own temperature. And indeed, by following some work on Gibbons and Hawking, which dates back to like 50 years ago, we know that indeed there is also a first law of thermodynamics that we can associate to a cosmological horizon. It differs from a usual first law of black hole thermodynamics because we have a minus sign in front of this term here, meaning that if you throw in mass in the cosmological horizon, the area of the cosmological horizon actually decreases in size because there is a minus sign. So I will tell you a bit more about the thermodynamics of the cosmological horizon, but just let me give you a bit of a caveat that the fact that indeed we work with this under the assumption that indeed this law of thermodynamics is valid indeed. But of course, there are various subtleties in de Sitter space. One is for which you have a system like your space-time that contains the black hole and the cosmological horizon is not quite an equilibrium system, because in general, the temperature that you have at the black hole horizon is different than the temperature of the cosmological horizon. So you're not in a situation of equilibrium. Moreover, in de Sitter space, an asymptotic region where you can define charges, in particular when you can define a conserved mass, is lacking, because de Sitter doesn't have a space like a space like infinity. So as a definition of our conserved quantity, in particular for the mass, we will resort to the same concept that Gibbons and Hawking use, meaning that we define as the mass of our black hole the same quantity as will be the mass in a asymptotically flat space. This is something that we need to do in order to proceed with this treatment, even given the fact that indeed we have no asymptotic region at which we can define the Komar integral for our mass. Said this, so why also studying near extremal black holes? Well, because it was pointed out that in specific black hole regime, in this case in the near extremal regime, when a black hole has very little temperature, there are some interesting patterns arise. So for instance, the near extremal black holes were related to chaotic behavior by a seminal paper by Madasena, Stanford, and Young. So what we would like to do is to see whether the environment in which the black hole lives, so meaning once you put this black hole in presence of a positive cosmological constant, whether this cosmological constant can affect indeed the near horizon dynamics once the black hole is really kicked a bit outside the extremality. And we will see that for the Sitter black holes, given the fact that you have this cosmological horizon, there are new kinds of extremal and near extremal solutions. So there is much more physics with respect to what will happen, for instance, in ADS or in asymptotically flat space. And therefore, we are left to study how does the presence of the cosmological horizon modifies, for instance, the symmetries of a given solution and how the solution reacts once you really perturb it a bit. So the aim of this talk will be to, first of all, to study the allowed space of physical solutions of a black hole with charge in the Sitter space, and also how to perturb it away from extremality, and to see if we find some, for instance, some chaotic behavior or some Schwartzian action that describes the perturbations. So let me just start now with defining a bit of definitions. These are basic definitions about extremal and near extremal black holes in asymptotically flat space. So I'm showing here the static and spherically symmetric solution, which goes under the name Reister-Nordström in flat space. This is very simple, and I believe that all of you have seen it in a basic course of general relativity. So, but just to refresh your memory, this is a black hole which has a charge and a charge Q, electric charge Q, and also mass M. You will see that, so it's a solution which is spherically symmetric, and it has two horizons located at this particular radial coordinates, plus or minus. It has an outer horizon, R plus, and an inner horizon, which is R minus. And the extremal black hole is defined as the black hole with a minimal mass given a fixed charge. So in this case, you have that the mass is equal to Q. So because otherwise, this is a minimal mass that you can have. Otherwise, this thing at the square root becomes negative. So you have an imaginary value for the event horizons. So the minimal mass is the one which satisfies this relation. And at this point, an extremal black hole indeed has the two horizons that coincide, that we denoted by R0. So indeed, the two R plus equals R minus, and R0, which is equal to M, but is also equal to Q. In this case, you have, for instance, so as I mentioned, the two horizons coincide, and this is such that the black hole temperature is 0. So the black hole is stable, doesn't radiate. You can really see, because, well, there is a close formula for the temperature, but you see that it is basically proportional to R plus minus R minus. And once they coincide, you get 0. And the extremal solution in general has whatever dimensions. For instance, here is 4 dimensions, but also in general, if you go higher up, it's characterized in general by an enhancement of symmetry. So indeed, the near horizon geometry, once you zoom in close to the horizon, you have a geometry which is ADS2 times S2. So in higher dimension will be ADS2 times S3 or other kind of horizon geometry, horizon sections, let's say. And this symmetry enhancement for an extremal solution is also present once you have rotating black holes, for instance. In that case, you have the near horizon extremal neck, that I will talk about it probably towards the end, but it's not really the primary goal of this talk. But just to say that there is always an enhanced symmetry once you set the temperature to 0. Nevertheless, you have also the entropy of the black hole remains finite, and you have a huge degeneracy for the ground states. And in case where you have supersymmetry, you can even count states of strings on branes and reproduce the entropy of this black hole, at least in the setup in which you have an extremal black hole. So for near extremal black holes are solutions that are obtained when the two horizons are slightly separated from each other. So you take the solution that you had before, where R plus and R minus were both equal to R0, and you displace them with an infinitesimal parameter lambda, and you keep epsilon. Epsilon is a finite parameter which serves as a bookkeeping parameter. So you start from an extremal solution, you split a bit the two horizons, and the black hole automatically starts radiating, because indeed the temperature is proportional to this factor here, and the temperature becomes, again, infinitesimal but no zero. So it grows linearly with lambda. A different near horizon geometry appears, which is called nearly ADS2. I will explain, I will give a precise example later on of this. And this is considered as an excited state of the theory, because indeed it has a bit of a temperature. And the thing that the last few years, like studies of the last few years shown, is that there are some pretty much universal relations of how a black hole reacts once you kick it a bit outside extremality. For instance, the displacement, so the difference between the mass and the extremal mass, scales quadratically with temperature, with a parameter m gap. And also the same parameter appears here. So the entropy grows linearly with the temperature. These are formulas which were believed up to now to be fully general in whatever dimensions. Of course, this value of the parameters is dimension dependent and also depends on which kind of charges and angular momentum the solution has. But in general, this is the one that you have for ADS black holes and also Minkowski. We will see that this is different for the de Sitter black holes, and that's something that makes our what we find very interesting, because it is a signal of non-universality of this particular behavior. And what's the meaning of this parameter m gap? Basically, m gap has the meaning of excitations that you have above extremality. It's a scale that parameterized, like indeed the excitation energy that you have like on top of the extremal solution. It's an energy gap above the ground states in the microscopic spectrum of the black hole. It's also the energy up to which you, let's say, you trust your thermodynamic description of your system, because indeed you expect your, let's say, if you want to describe your black hole as a thermodynamic system, you want indeed that the black hole evaporation to be a quasi-adiabatic process, and if the difference in mass of the black hole is equal to m gap, a Hawking quanta will carry away the entire energy of the system. This is something that you don't want. So you can trust the thermodynamics up to m that goes on like up to m, which is bigger than m gap. So again, another face of this coin is that indeed you can just fully work out this thermodynamic relation starting from, as I was mentioning before, from the 4D point of view, but you can also, all these excitations have a description in terms of models of JT gravity. So indeed the reduction of on S2 of this system, which is Einstein-Maxwell, gives rise to models of JT gravity, which indeed are characterized by the presence of a dilaton, which multiplies the Ricci scalar, and also have indeed like this sort of very general, let's say, very general action. And so these models here indeed parameterize or like describe the excitations above extremality of an extremal black holes, and they were extensively studied in the context of the near ADS2, near CFT1 correspondence, which describe the conformal symmetry breaking in ADS2, which are really used, which really happens once you indeed you go beyond extremality. And finding solutions from dilaton and also for the metric perturbation, it really shows how, by following this setup, you can really see how the geometry extends away from the near horizon geometry. And by checking the fall of the dilaton, by finding again the solution of the dilaton, you can really see that in the dual field theory, there is a mode of the dilaton that corresponds to an irrelevant operator in the IR theory. So that also adds to the dynamics of the theory. And as I was mentioning probably before, so these JT gravity model, these particular kinds of models, which goes under the name of JT gravity, also exhibit the same symmetry breaking pattern, which is realized in systems as a SYK model, which are quantum mechanical systems, which are ensemble of quantum mechanical systems. So, okay, this is the picture that we had for just asymptotically flat black holes. They are fairly well understood. And all this, the dynamics of these black holes, which are near extremal, were also related to chaotic system and so on and so forth. Now we want to see what happens for de Sitter black holes, because for de Sitter black holes, we also have the outer horizon, which can in principle modify this picture. So we consider then Einstein theory, which is just Einstein-Maxwell lambda with as I was mentioning before, a positive cosmological constant. And we look again for statically and spherically symmetric solutions because they are the easiest ones. So what we have is then the Reister-Nostrom de Sitter black hole, which indeed has this sort of metric with the warp factor, which is this one. So notice that the appearance of a cosmological constant manifests itself into the presence of this term. So before we only had these three terms, but now you have another one, which means that the warp factor is a quartic polynomial instead of a second order polynomial, which means that in principle we have up to 4 roots. 4 roots, which means that you have up to 4 horizons. In the case under consideration, one of the roots, we find that one of the roots is always negative. So RC2 is always at a negative radial coordinate, so it doesn't enter our analysis. But the other 3, we denote them as R minus, R plus, and RC. RC will be the cosmological horizon. This is really outside. R plus is the outer black hole horizon, and R minus is the inner horizon. So when you have lambda goes to 0, this becomes the original Reister-Nostrom solution, which you have only the outer and the inner horizon. So we studied indeed the phase diagram for black holes, and the phase diagram has a funny name, which is called the shark fin. So it's like the fish that has a fin. So let me just draw it here. So I draw here the mass and the charge, which for simplicity I take it to be positive, but of course, otherwise it's like the diagram is just flipped. So the shark fin has this shape here. So inside this region, you have very regular black hole solutions, and outside here you always have naked singularities. This was already found by Romans. So this area here is bounded by some lines, which here I put like the dashed. So the outer line in which, so we are seeing that we have 3 horizons, so we can make 2 by 2 coincidence, so that will be different extremal limits that we have. So at the upper edge of the fin, we have the cold black holes, which are characterized by having R plus equals R minus. They are the solution that most resemble to the extremal Reister-Nostrom in flat space. The other edge of the fin, they are the Nari-I configurations, so-called Nari-I, in which the cosmological horizon is equal to the outer horizon, and also where the 2 lines meet is the ultra cold point, where R plus equals R minus and also equals RC. So this is just a very special point that fixes all the parameters together. So what we're going to do is we are going to try and see for all these three different extremal limits, what will be this universal relation that describes the thermodynamic response for the black hole up to when you change a bit the temperature. So first, we can then deal with the cold black hole, so the upper edge of the fin. So for this black hole, we have that indeed, so R plus is equals R minus, and we denote it with R0. And it needs to have in order for this configuration to be regular, you need to, you have a bound on the value of R0. And so the warp factor then develops a second, a root, like a double root here. And in order to have a cold solution, the parameters need to satisfy these 2 relations here. So what you do to find the new horizon geometry is that you develop, you engineer the coupling limit, which is fairly simple. So you zoom in into the horizon and you rescale also the time component. This effectively brings you really close to the horizon, and the new horizon geometry is ADS2 times S2. So where the radius of ADS2 is different than the radius of R0 in general, is different than the radius of the sphere. While for Minkowski, these 2 radii are indeed equal. But in general, the geometry is still like a product of ADS2 times S2, so it really resembles the one that you have for Minkowski black holes. So what you're going to do in order to heat up the black hole, basically you want to displace the 2 horizons, as I was mentioning before, and you want to move horizontally inside the fin. So basically you start from a cold solution in this, let's say this one, and you want to displace the horizon in such a way that you enter inside the fin, and you reach a configuration with a bit of temperature. So you have to move horizontally in an ensemble with Q, which is fixed. So as I was mentioning before, so we displace the 2 horizons here, and the near horizon metric is a new geometry, which is called near ADS2 times S2, which is this one. So we can, after we have seen what is the near horizon geometry, we can now see what is the temperature of the black hole. So we can compute it easily with formulas that we have at hand. And we see that again, the temperature scales linear in lambda, And we can also compute the mass gap. So we have a formula for this parameter here, which indeed is positive. So these relations here are the ones that are satisfied. They are similar to the ones that you have in asymptotically flat, but you can compute the mass gap, and the mass gap is positive indeed, because if you increase the temperature, you also increase the black hole mass. And also notice that for the black hole, like at the cosmological horizon instead varies at second order in lambda. So we are in an ensemble in which the cosmological horizons stay fixed, but we just vary the two horizons which are internal, like related to the black hole. So for the Nariai geometry, like situation is again, so the Nariai geometry is the lower part of the fin, and we have this constraint here that R plus is equal to RC. So the cosmological horizon is equal to the outer horizon, and the constraint is opposite with respect to what we had before. So R0 needs to be bigger than a specific value, which depends on the cosmological constant. So performing a similar decoupling limit, you have a new horizon geometry, which is again ds2 times s2. Well, sorry, which is not ADS2, but DS2 times S2. So there is an appearance of de Sitter 2, like two-dimensional de Sitter space. And once you separate the two horizons, again, the decoupling limit gives geometry in which, again, epsilon appears, and it's called near DS2 times S2. We computed also the entropy change and the change in mass. And this also like give a value of the mass gap, which is formally equivalent to what we had before. However, now, in order to have a well-defined solution, we have that R0 needs to be greater than lambda. Therefore, we have a negative value of the mass gap for the cosmological horizon. And indeed, we see that this is reflected also from the fact that from here, if we work in an ensemble of fixed charge, for instance, start from an area configuration, you can just go inside the fin this way, because if you go inside this way, you hit an equisingularity. So you have to move along this line, horizontal line inside here, which means that the mass needs to decrease. That's why the mass gap is indeed negative. The most interesting, so the value of the mass gap, however, is kind of formally equivalent, like at least in formula, to the ones that we had before. However, the very interesting new case is the ultra-cold solution, where the three horizons coincide. So this solution is characterized by these precise parameters, just one point in the phase space. And once you start from, so the ultra-cold solution, the work factor has three coincident roots. Therefore, if you want a well-defined decoupling limit, you cannot do any more zooming procedure, which is linear in lambda, but the lambda needs to be to the power 3/2. This is something that you can play around, but to have a well-defined limit, it seems that this is the only option. So sending lambda goes to 0, we see that the new horizon geometry is not ADS2, is not DS2, but it's Minkowski 2 times S2. So it's really this simple one. And yeah, this is very peculiar to the fact that we have a de Sitter black hole. This case here doesn't arise in other sort of cosmological scenarios. So what we do to heat up the ultra-cold solution? Well, so we are here at this point here, like just at the tip here. So if we want to reach a solution which has a bit of temperature, we cannot move horizontally here, horizontally there, because we will hit an equisingularity. We have to move along this line here. So we have to move diagonally, which means that we will need to move Q and M separately. So we need to both move Q and M. What we actually managed to do, we stay really, really close to the ultra-cold point, because what we'll see is that, so we try to displace the three horizons. So our aim is to check what happens if we display the three horizons. So we introduce two parameters, W1 and W2, and also the infinity, which are the bookkeeping parameters. We also displace them with the value of lambda, which is infinitesimal. And we have that indeed, in this case, the temperature variation is of order lambda squared. So this solution is really, really cold. So even if you displace the two horizons by the same amount as you were doing in the cold and in the Nariai case, in this case, the solution is very, very cold, meaning that the solution doesn't really heat up only at second order, which is something that indeed it's our setup is not sensible to. So the new horizon geometry, if we call omega 1 equals epsilon and setting omega 2 equals to 0, is this geometry here, and the presence of epsilon is trivial, so it can be completely reabsorbed via scaling of T and R. And if you plug in the value for R plus, RC, and R minus in your thermodynamic quantities, you get that also the mass and the charge do not change at linear order. However, the entropy changes, and the fact that you have, and the fact that it changes is due to the fact that you change not the mass, not Q, but you change indeed the chemical potential of your theory. So the change in entropy is indeed driven by a change in chemical potential and not really by a change in temperature, because the temperature was staying of order lambda square, so it was staying constant. So let me just recap for a moment before going to the 2D, corroborating this picture with the 2D analysis. So we see that for the cold and area geometry, we managed to compute these response coefficients. And the geometries can be heated up, meaning that you take the two horizons, you split them with respect to the extremal configuration, and you get this sort of response coefficient for the entropy and for the mass with a value of n gap that we have a formula for that, like it's very clear. For the ultra-cold geometries, instead, we have proven that when the two horizons are displaced from extremality, the entropy the temperature exhibits a subleading response, meaning that it's quadratic in lambda, but the entropy changes because the chemical potential changes. And this is really reminiscent to other studies of 2D gravity in flat space made by Grumiller and the area group in Vienna, which show that indeed you have a specific heat in studies of 2D gravity in flat space. The specific heat is indeed infinite when you set the charge to be constant. So this is what we have found from the thermodynamics of the 4D solutions. Now I'm going to try to corroborate this picture from the 2D analysis, unless there are questions. Okay, if not, I will go on with the 2D analysis. So as I was mentioning, we have found the solution just from the 4D configurations. Now there is another way to get, like, to see if this behavior is correct by checking the perturbation that you have in the theory, which you find by reducing to 2 dimensions. So indeed, that's what we do. So at least we perform dimensional reduction of Einstein-Maxwell on the sphere with a metric which is of this form here, in which the sphere is factored out here, and the size of the sphere is proportional to the dilaton, as I was mentioning before. And moreover, we found, we impose that the field strength has only component along t and r direction. So the action that you get in 2 dimensions is indeed this one, which is of the same form, of a similar form with respect to, it shares many features, let's say, with models of JT gravity, and also with other models of dilaton gravity in 2 dimensions, such as the Kallan-Giddings-Harvey-Strominger model, and the same model, but once we incorporate also some other vector fields and some other auxiliary fields, which are called, and the same models that extend this one are called GG-HS-AT model. So what we did is that, okay, so we start from this action here, we compute the equations of motion, and the equations of motion give us geometries, which are indeed like 2-dimensional geometry with constant curvature, which is given by this value here. So the curvature can be indeed positive, negative, or 0. As the near horizon geometry that we start from is Minkowski 2 times S2, DS2 times S2, and ADS2 times S2. So these are the near horizon geometries for which we started from our black hole. And we compute the perturbations on top of these near horizon geometries. So we perturb, we consider linear perturbations of the field, which is the dilaton, of the metric, and also of the gauge field. So we plug this value here inside the equations of motion that you get from this action here. And then we linearize, we take the leading order in lambda, so linear order in lambda, and we get these equations for the perturbations. The first equation goes under the name JT, or JT equations, and the second equation is just the equation for the metric perturbation. So now we have to find solutions to these equations and see how they behave in order to see if we computed well the mass gap and the thermodynamic response that we have found before. So we do exactly the same for the 3 cases, cold, Nari, and ultra-cold solution. So for the perturbation of cold, then, we start then with a background 2-dimensional geometry, which is ADS2. So this is the background metric, which is ADS2, but also we consider a more general form for ADS2, which is indeed considering also a diffeomorphism, which is still dependent on ADS2. So we have a more general background metric. And the solution for the equation that I showed you before can be easily found because we can adapt the procedure of Maldacena, Stanford, and Young. And we also set delta Q to be 0 because in the case of the cold black hole, we could just enter the fin just without staying in the horizontal line. So the dilaton indeed has this particular fall-off in which we see indeed that there is a divergent term which corresponds to the irrelevant operator in the dual field theory. And depends on on two functions, mu and theta. And you can find a closed solution for the perturbations that we decided to indeed display, or we decide to solve in function, like we decided to solve for beta and theta in function of the other two functions, alpha and mu. And also we have a fully explicit solution for the metric perturbation. So these are the equations that you get from the 2D metric. They're all parameterized in terms of only two functions, alpha and mu. So now we are ready to see, like, to compute the thermodynamics from the two-dimensional point of view. So to the background metric, we can associate indeed a temperature and an entropy. So the temperature is readily computed as the derivative at the zero of this function gamma that appeared in the near horizon metric. And the two-dimensional entropy instead is given by the value of the dilaton at the horizon, including the first order perturbation. So from this particular analysis, we could see that indeed they agree with the 4D relation that I was showing you in the previous part of the talk. So we corroborate indeed the fact that the mass gap that we found from the 4D thermodynamics coincides by the one that we get by solving the perturbations in the near horizon geometry. Moreover, we have seen also that we have computed the normalized on-shell action in 2 dimensions. And we saw again that indeed the linear response in temperature comes from an effective Schwarzian action, in which indeed this coefficient here is proportional to the coupling in front of the action. So we also verified again that the value of M gap is the same one as we found before by computing also the on-shell action and deriving the entropy, which is proportional to the term with the Schwarzian. So again, so this for the cold seems everything is consistent. For the Nariai case, which is the case in which we have the DS2 near horizon geometry, stuff is a bit more, let's say, it's a bit more tricky because from the two-dimensional point of view, we managed to get the perturbation. So we could manage to find solutions to the JT equations and the metric perturbation here. Because the solutions are formally equivalent to the cold ones, you have to perform specific Euclidean continuation, but the two solutions are related, so we have the same, again, a dilaton which diverges, and it is function of two functions for which we can find a closed form. Notice that we have used a metric, which is DS2 in the inflationary patch. But what we would like to see, so the inflationary patch is a metric that indeed doesn't exhibit a horizon. What we will need to do is to find a background metric which really relates to the static patch of the sitter, the one that really exhibits a horizon. So we can get the metric in the de Sitter patch by choosing this particular form for the coefficients, which plug here, and by changing the coordinates in this way. So what we get is a metric which is very similar, like formally equivalent to the DS2 static patch, but in which R is bigger than LADS. So we are actually, from this kind of procedure, we are actually outside the static patch. So we are outside the cosmological horizon. So and solution is still linear in the dilaton. There still is a divergence, but we would like to find a solution with R which is less than the cosmological radius. So this is something that is still work in progress. But what so far we have shown is that indeed a metric like this one can be obtained by a suitable near extremal limit starting from the Naria configuration. So we have also verified again what other people indeed were finding from their own two-dimensional analysis. And if we want to get solution in the static patch, we will need to start with a different background metric, impose some reality conditions on the function beta and alpha that we found here. And this is something that with Francesca is still work in progress. But at least up to now, what we have found indeed that the solutions are there, and we have solved for the solutions. Computing the renormalized on-shell action for backgrounds which are de Sitter is a bit tricky because you don't have really like a very well-established procedure of holographic normalization. So this is something that is still work in progress, but at least we have the first step, which are the solutions. So now we come to the last point. The last point is the perturbations for the ultra cold solution, which is the one for which you have a metric, which is Minkowski 2 times S2. And so what we did is that we started from a Minkowski 2 metric, which is written in terms of Eddington-Finkelstein coordinates. So these coordinates are r hat and u. And we decided to make an ansatz for the perturbation, which is an ansatz for the dilaton, which is linear in R, and also with a constant piece in R, which depends only on the retarded coordinate u. And the equations for the perturbation are crystallized in these two very simple equations here, plus an equation for the metric perturbation. So in general, simple to solve, especially if you put some specific values for the two parameters, so for the two functions which appear in the background metric, P of u and T of u. For instance, if you set these two functions to be constant, and in particular P0 equals 0, the solution for the functions appearing in the dilaton, they are very simple. So you can solve the equations for the perturbation, and you find this very two simple form. And if you want static U-independent solutions, because in general, that's the one that explicitly match the decoupling limit that you get for the ultra cold that we found before, you have to set delta Q equals B1 equals 0. So these solutions here are directly connected to the ultra cold geometry. However, there are also another branch of solution in which you have to, from scratch, set that P0 is different than 0, and tau, and big T 0 is just constant. So you see that now you can find a different set of solutions in which, okay, you cannot take P0 to 0 because it lies at the denominator. And this is another detached, very different solution that you find from the same 2D model. And it's detached from the black hole. It doesn't really relate to the black hole that we found before as the decoupling limit. And again, can be static, and indeed can have delta Q equals 0. But once you even if you impose delta Q different than 0, becomes independent of the background metric at fixed charge. So if you set delta Q equals to 0, the solution here doesn't depend anymore on the background metric. And this is very different with respect to what happens in the cold and in the Nariai case. So this ultra cold point is really very specific. So if you impose, moreover, if we want that the dilaton has a linear behavior in R, mainly boundary condition of this form, then we have to relate the change in charge with respect to this leading coefficient phi R. So arbitrary charge variations are not allowed. So this is a boundary condition that you might want to impose. And now we are ready to see, so we have found two solutions. These ones, which are more general, and the previous solutions, which are directly connected to the black hole. Once we found these two solutions, now we want to check the thermodynamics that these solutions give in 2D. So since we only work with static solutions in which P0 and T0 are independent of U, the background matrix simplifies a lot into this form. So, and in 2D, this corresponds to having a black hole solution with RH equals minus T0 over P0, for which we can readily compute the Hawking temperature, and we find it to be proportional to the parameter P0. So we've seen, first of all, the fact that for branch 1, the temperature is always 0. So branch 1 is always cold, but branch 2 of solutions in which P0 was non-zero can actually be warm, so can have a non-zero temperature. And the solution for the dilaton is 1, which is just a constant value for the dilaton. And for branch 2, there is a piece which indeed varies with R. So we have computed now the temperature. What we need to do is to compute the entropy, which is readily computed once again by expanding the value of the dilaton at linear order in lambda. So we have a piece in the entropy which corresponds to the extremal entropy, and we have the response to the temperature, which is here. So indeed, we see that for branch 1 is it's consistent with the ultra cold thermodynamics, because indeed there is no change in entropy due to the temperature. So this is something that we've seen, and we indeed saw what we had indeed from if you remember, from the thermodynamics point of view, from the 4D point of view, we didn't find any change in entropy because due to temperature. So for the second term, instead, it's very particular, and it's due to the fact that we have a second branch of solutions. And the second term does not have a smooth limit for t equals 0. So if t equals 0 here, then you find a divergent part. Unless you impose from scratch that this t0 is 0, or you modify the boundary conditions such a way that this delta q is proportional to t squared. But this is something that is a bit tricky to implement in your two-dimensional analysis. So we also corroborated this by computing the two-dimensional renormalized on-shell action, which assumes this form here. And for constant values of the parameters appearing in the background metric, we have indeed a value of the on-shell action, which is such that if you compute the entropy, you see that indeed the temperature doesn't affect the entropy, and in particular doesn't affect the on-shell action. So this is very different than what happens to the cold and REI, where the temperature was the leading effect of the formation. So by all these two-dimensional analysis, we reproduced, at least for one of the branches, the fact that if you displace the two horizons, if you compute this linearized perturbation, the entropy changes, but it actually doesn't depend on the temperature. So, okay, so I reach now to the conclusion. I think there were not that many questions, but maybe it's because we are all after lunch, but so I'm a bit early. But okay, so what we have done so far is that we have checked the behavior of this like linear response to black holes once they are kicked out of extremality, and we have used a toy model, which is the one of the sitter black holes, and we have investigated how the environment that contains the black hole indeed affects the thermodynamics and the response, like once you break away from extremality. And the fact of a positive cosmological constant is that you could have an outer, like a cosmological horizon, and gave you three different extremal limits, as I was mentioned, the cold, the Nariai, and the ultra cold. And especially in the ultra cold case, we had a very different thermodynamics behavior with respect to what you had in the other two cases. So what we could do now, for instance, is that so far we have seen that the behavior of perturbations like which are linear in lambda. But if we want, for instance, in the ultra cold case to actually enter the fin, so you remember that if we just displace the horizon linearly with lambda, the mass and the charge were really like we were staying around this point. But if including higher order, like going beyond linear order, we will actually manage to enter the shark fin and really get into access to the point inside here. Moreover, we could see if there is any particular different, thermodynamic behavior for black holes in de Sitter, which have, for instance, in higher dimensions. In this case, the warp factor will have a different numbers of roots, and that could give you more physics or even more extremal limits in general. And moreover, for the Sitter black hole was recently found a bound which generalized the bound of the weak gravity conjecture to include, for instance, the effect of the cosmological constant. And I believe that since we have a model of 2D, by adding charge matter to our model of 2D gravity, we could actually try to see if we find the same bound as the Festina lente that characterize indeed the black hole evaporation in the Sitter. And as a last step, I'm just mentioning the fact that this procedure can also be adapted to the case of Kerr de Sitter black holes. So also for Kerr de Sitter black holes, from our preliminary study, we see that there is a shark fin. So again, here we plotted the J, so the parameter A, which is proportional to the angular momentum, and this is the mass. So again, the solution is much more complicated. It's not anymore spherically symmetric, but it seems that indeed you still have lots of different, you still have three different extremal limits. You still have the cold, the Nariai, and the ultra cold. And you can have a rotating Nariai as well. Yes. It's just a bit different. And for the Nariai rotating case, actually, these people here, Aninos and Hartmann, managed to reproduce the black hole entropy via computation, which comes from the Kerr CFT correspondence. So by computing, let's say, the conserved charges, and then by deriving a central charge of the dual CFT in 2 dimensions. So in all these rotating cases, I think one of the very interesting aspects of this rotating extremal black holes in the sitter is that you have a handle via the Kerr CFT correspondence. So indeed, with the Kerr CFT correspondence associate to a near horizon of an extremal rotating black hole, a 2D CFT. So it's something that for us instead, in the previous case, the previous cases, let's say the dual field theory of a near extremal black hole is this models of SYK, this kind of disordered model of one-dimensional quantum mechanics. But now you have the additional picture that comes from the Kerr CFT that relates all these features of the black hole to a 2D CFT. So that's something that we are in the process of elaborating. Of course, once you compute the perturbations of the metric and the dilaton and so on, you cannot use anymore the ansatz that I showed you here before, these ansatz here, because this is only for spherical symmetric configurations. So you'll need to engineer something much more complicated, because you have to account for the fact that your metric depends on the coordinate theta. But this is something that is, again, work in progress, and there was some related work by Alejandra and her student for asymptotically flat black holes. So with Francesca, which is a PhD student in Ghent, we are trying to, let's say, extend all these considerations to the case where you have angular momentum. So, okay, this is like all what I wanted to say.
So in this case, in this case, you will have the Killian tensor, which induces hidden symmetry.
Yeah, you will have some hidden symmetry, yes, from the Killian tensor, but here I think what we are trying to do now is that to avoid reducing this theory to 2D, but just computing the perturbation directly in 4D. So I don't know, for that probably the Killian tensor might be useful or not. I don't know, probably.
Tells you how you change the expansion harmonics.
Okay, yes. So in general, yes, the approach that we are using is a bit more pedestrian, let's say, imposing that the perturbation depend only on R and theta, and we made a very suitable ansatz for some the angular dependence, because these people already found a very particular truncation. But yes, if you want to find something more general, then you could use your method, I think.
Let's say the lowest, you truncate the spherical harmonics.
Exactly, yes. Yes. Via the Killian tensor, you mean? Okay. Probably, okay, we're going to have a look at that. What we had in mind was a bit simpler and heavily drawn from this paper. But in principle, you could do it. Yes, the point is that, yes, let's say, so the point is that, yeah, you have to tune your parameter in such a way that you have a near extremal, you're close to extremality, but yeah. So another case in which we could do is to try to add also charge. In that case, you can also have charge and angular momentum, so you can treat, again, like you can fix the extremality and extremality via the charge and then treat the angular momentum as a perturbation. Yes, you can do that as well. For the moment, we are trying to just add angular momentum and see how things change. And already at the point of view of the 4D perturbations, it's a bit more heavy, so that's why we have to relate. We have to rely on some previous work which have particular answers.
Other questions?
In the reduction from 4D to 2D, could one also introduce the KK values?
Yes, in principle, yes, but they will have a higher mass, right? So it will be further fields to take into consideration, but we kept only the massless case. Sorry, they would not be. I think in that case you will have a mass for them, right? Or maybe I don't know if I'm mistaken. Like, I mean, I don't know if you, I don't know if what you meant. You mean the tower with all the mass of the Kaluza-Klein modes? Yeah, here we are restricted to just the lower ones. Yeah, so this is the minimum amount of matter that is necessary to produce a near extremal deformation. So basically what we want to start from the spherical, we want to keep the spherical symmetry because we would like these ansatz to describe an extremal black hole, but also a non-extremal black hole with the same symmetry. That's why we did not include any matter that would allow some deformation of the sphere or so on. But I'm not okay, maybe we can talk later. I'm not sure that if that this was what you meant, but we try to keep the same symmetry, extremal, near extremal, just the minimal deformation.
Other questions, comments? Maybe I can ask, what about the stability of this solution? Can you say something? You do perturbation, can you derive something about the stability of these solutions?
Let's see, like, well, I guess that in a way, yeah, you could try to, yeah, let's say for the moment we have tried to figure out, so the perturbations are with a specific, let's say, they are within a specific ansatz that are really like perturbations, you know, we linearized on top of the IR geometry, which is a geometry with the, you know, with fixed curvature. So it's either ADS2 times S2 or DS2 times S2, but you say perturbing the full geometry. That's what you mean to see.
Yeah,
Yes.
The global stability.
Yes, that would be, I think, yeah, for that it's much more complicated. I would say this is just like literally a mode which is very spherically symmetric and everything. There are for sure people doing that. I know some, I think, for instance, I think George Santos and so on, like these people really study stability of especially near extremal de Sitter black holes in relation to the, I think, to the strong, like for the cosmic censorship conjecture, I think. But there I mean, George Santos worked usually with this Einstein-de-Turck method, so it's like the perturbation that he finds are very much like you need other techniques, I think, for that. I mean, yeah, I think it's much more difficult with respect to what we have found now, but in principle, you could try to perturb the full geometry. But yes, it's out. I mean, with our technique, it's just much more simple to find it like the perturbations over ADS2, DS2, or Minkowski 2. So they are just a bit, our procedure is just more limited to the near-Horizon geometry. And the other instability that I was mentioning was the one related to the Festina lente bound. And but this is more like an instability towards like when you take into account you know, quantum effects and Schwinger pair productions. So you will need to include, for instance, you will need to include a charge field into these equations here, with a specific bound on its mass and charge, which allow for, which also involves the cosmological constant. And you will basically, so what Miguel Montero in this Festina lente bound is basically finds a bound on the mass and the charge of this charge scalar field in such a way that all the black holes, the Nari black hole and the cold black hole, eventually discharge into the zero charge solution. So there is another instability, but this is instability related to Schwinger pair production. You could see, I think, also this if you add a charge scalar field in our procedure. But that's another.
So you perturb your solution with a charge scalar field.
Yes, it would be. It would be that pretty much. But with a charge scalar field that satisfies the Festina lente bound. That should give you, should give you dynamics in such a way that all these black holes should discharge eventually to this point here, because that's what people, basically people that do swampland and so on don't want extremal black holes because they are remnant. So they want them eventually to kind of discharge fully. And that's what the Festina lente bound pretty much tries. Like it's a condition for this to happen while remaining into the shark fin. We didn't look at this yet.
Please. Kind of talking about the stability in the superspace. Some time ago, there was polycon. to argue that there is some physical instability in the superspace.
Okay.
Could you comment on this? Is it related to what you're talking about change of pair production, or is it different?
I don't actually.
His point was to say that if you just try to formulate something quantum in the zeta space,
Okay.
as soon as you start talking about quantum, the vacuum in the zeta space is not stable.
Okay, I see.
He argued that basically it doesn't matter, which would be a classical background black hole, because there is instability, the back reaction of the system, well, quantification will act back on the journey.
Okay, I see. Yeah, I'm not aware of, I mean, I don't think I can comment with anything useful in that, but yeah, in our case, it's difficult to say because just we started already from the configuration which have black holes, and we work mostly at fixed charge ensemble, so it doesn't, I mean, we really cannot make contact with, I mean, if you fix the charge, then you don't have pure de Sitter anymore, right? So we cannot really see, I mean, at least from our setup, it's kind of hard to get anything for that.
You will not have source for this instability. You will not have quantum fields which will create on your background.
Oh no, for sure. In our procedure, no. I mean, it's not quite, the quantum fluctuation would be like a, yeah, you will need to.
Just this pure picture, no source for that.
Yeah, but then what Parikubicek was asking is that even you identify the classical solution where the black hole.
So you're saying,
quantum corrections would destroy the fluctuation.
okay, could be, but we didn't, I mean, yeah.
Even more naive question, because your black hole seems to be huge, yeah, compared to the level.
Exactly, at least the Nariai, yes, because
universe. So what is the sense of studying entropy and
no, okay, this is like, so for instance, in this, yeah, of course, for the Nariai case, this black hole is huge, yes, because it has the same size as the cosmological horizon. So indeed, we don't want that. It doesn't reflect something that we have in our world. It's a highly idealized setup. But for instance, the cold black hole or an extremal black hole in de Sitter, I mean, we have a small cosmological constant today, so it's worth studying. The Nariai, no, also the concept of negative mass gap is something a bit, it's not quite something that you would consider physical as a mass on top of the ground state if it's a negative mass gap. So for sure not. It's not something that would describe a realistic black hole. Just from the formal point of view of the symmetries and so on, then you can still study. Of course, it's a, yeah, it won't be something that will appear in our universe, something which is like a black hole with the size of our universe. At least we hope not. But for the cold one, I think it's, especially if you add rotation, I think it's something that it's very, it's worth studying. I mean, but yes, for our stuff is not quantum at this point, so I cannot really like say too much about that.
More questions, comments? Okay, so if not, we thank Chiara again.
Okay.
The coffee is upstairs, and we resume at 4 for the talk by Joanna.